Modern industrial systems, from electric vehicle drivetrains to solar power arrays, run on a strict mathematical demand. They frequently require taking a low input voltage, like 24.5 volts, and immediately stepping it up to 200 volts to perform actual heavy-duty work. Pushing a standard boost converter to a 1:8 ratio forces the switching components to operate at their absolute thermal limits. At 50,000 cycles per second, the cumulative heat buildup leads to rapid efficiency degradation and eventual semiconductor failure. Standard topologies fail here because of two unavoidable parasitic enemies: massive voltage stress across the components and high switching losses, energy burned away as heat every time a switch forces its way between on and off states. Bypassing those thermal limits requires a different architecture. This schematic outlines a single-switch resonant converter. Notice the highlighted section. We've replaced brute force with a carefully tuned resonant tank. The target specifications for this design are precise. Take a 24.5-volt input and deliver a stable 200-volt output, driving 200 watts of power into the load. Simulated under those exact parameters, this topology reaches a peak efficiency rating of 96.6%. That minimal energy loss is achieved through a technique known as soft switching. Scaling up voltage without destroying the silicon requires moving away from traditional heart switching mechanics. We have to let the natural oscillation of a tuned resonant tank do the work. A resonant tank operates by isolating energy in specific reactive components. In this circuit, that means two resonant inductors and two resonant capacitors. The values of these components aren't random. Their combined inductance and capacitance are mathematically selected, so their natural oscillating frequency matches the 50 kHz switching frequency of the main circuit. Let's track the steady-state operation. During the first interval, T0 to T1, the main switch Q is clamped in the on position. Capacitor CR1 takes this opportunity to discharge its stored energy directly into the secondary resonant loop, feeding capacitor CR2 and inductor LR2. Moving into interval T1 to T2, switch Q opens. With the main power path cut, the energy now bounces back and forth between CR2 and LR2 naturally. To keep this loop intact without the main switch, diode DP conducts on its own, ensuring the resonant exchange of energy continues uninterrupted. Interval T2 to T3 is where the actual power delivery happens. The current path reverses, bypasses the internal loop, and flows completely out of the resonant tank. It passes straight through the output diode, delivering the accumulated high-voltage energy directly to the 200-ohm load. Finally, in interval T3 to T4, the system resets. The input inductor pulls current from the source to recharge CR1. That recharge perfectly primes the tank, filling it with exactly enough energy to repeat the cycle when the next 50 kHz pulse arrives. By using physics to naturally bounce energy between components, the circuit dictates the exact moments when voltage and current hit zero. That precise timing is what makes lossless switching possible. To prove this soft switching is actually happening, we look for two specific events: zero current switching, or ZCS, when the switch turns on, and zero voltage switching, or ZVS, when it turns off. Look at this multi-line graph from the LTspice simulation. At the exact microsecond the square gate pulse goes high to turn the MOSFET on, follow the vertical alignment down to the drain current. Because the current is at virtually 0 amperes when the switch engages, there is no massive power spike. ZCS is successfully achieved. Now analyze the turn-off phase. Watch the drain voltage curve. It plummets to 0 volts slightly before the gate pulse finishes its cycle and drops low. Capacitor CR1 effectively pulls the switch voltage down to 0 early. By the time the gate actually closes, there is no voltage left to fight against. Zero voltage switching is verified. Perfectly timing these zero crossings solves the heat problem. The RMS current on the switch is restricted to roughly 1.8 amps. This drops conduction losses to 11 milliwatts, keeping the MOSFET well within its safe operating area. If this architecture works so well, why not scale it up for massive industrial loads by replacing the MOSFET with a heavy-duty insulated gate bipolar transistor, or IGBT? These side-by-side simulation plots show what happens when you run that exact experiment at 50 kHz. The left is the clean MOSFET output. The right is the result of swapping in an IGBT. The hardware substitution immediately breaks the system. The output voltage exhibits massive ripple, severe waveform distortion, and incredibly slow rise times. The root failure comes down to semiconductor physics. IGBT architecture suffers from an intrinsic phenomenon called tail current. When the device receives the signal to turn off, the electrons don't clear the channel instantly. They trickle to a halt. At 50,000 cycles per second, the IGBT physically cannot clear that tail current before the next switching pulse arrives. The gate is effectively jammed open, destroying the zero voltage timing we just established. To successfully utilize an IGBT's high voltage capabilities, the entire system frequency must be throttled down to the 10 to 20 kHz range. High-frequency resonant topologies cannot be brute forced. Your component selection has to respect the exact physical timing limits of the resonant tank. So far, this system is running strictly open loop. If the input voltage fluctuates even slightly, or if the load resistance drops, the 200-volt output will drift off target. To make this viable outside of a simulation, we have to build a closed-loop digital feedback system to dynamically regulate the output. Look at this block diagram mapping the control path. The first step in that loop requires reading the output voltage, but we have to isolate the actual DC value from the high-frequency switching noise. We route the raw output through a simple RC low-pass filter. It physically attenuates the high-frequency components and outputs a clean, stable DC analog signal. But a modern microcontroller can't process a continuous analog wave. We have to discretize the data. That clean signal is fed into an analog-to-digital converter. The ADC samples the voltage at discrete time intervals, slicing the physical wave into raw digital numbers. Now the microcontroller can run the logic. It takes that sampled number, subtracts it from our hard-coded 200-volt reference target, and generates an exact error signal. A proportional integral derivative, or PID controller, instantly reads that error. If the voltage is too low, the PID mathematically calculates the difference and widens the PWM duty cycle on the MOSFET to compensate. If it's too high, it narrows the pulse. Without this pipeline of signal conditioning and active digital math, the raw efficiency of the resonant tank is uncontrollable, rendering it useless for precision electronics. Looking at the complete architecture, the system relies on two distinct halves. The left side handles the raw physics of power transfer, while the right side handles the logic of stabilization. The passive components in the resonant LC tank guarantee the precise zero-crossing timing needed to eliminate high-frequency switching losses. Simultaneously, the digital PID loop monitors the output, adjusting the duty cycle on the fly, so the hardware rigidly tracks that 200-volt reference, despite real-world environmental variables. Forcing a 24.5-volt input to reliably step up to an industrial-grade 200 volts requires exactly this kind of unified, closed-loop architecture. This LTspice simulation provides the direct mathematical foundation for programming physical microcontrollers like an STM32 by identifying the specific filter constants and PID timings required for the hardware. By accurately simulating the interactions between the single-switch resonant tank and the digital control loop, engineers can bridge the gap between theoretical power electronics and the physical demands of next-generation green energy infrastructure.